So yesterday we discussed about the diode equation, and you've learned before that the equation says that J is equal to J naught times exponential QV over KT minus 1. Okay, and we've learned a little bit about interpretation of the equation yesterday. As far as the PN junction is concerned in forward bias and reverse bias, and then what is actually happening on the graph, right? So before this, probably the way you saw the graph is very simplistic, I would say. When you look at the forward bias region, you just can see that the current increases exponentially when the voltage is high enough, and the current is very low in the small negative region in the reverse bias. But when you learn about this course, now you know that what is actually driving what you see on the graph. So for example, if you're applying the forward bias, so we are actually reducing the effective Berry height at the PN junction region, right? Or at the depletion region, to be more specific. So that will induce the carriers to flow again, right? The diffusion of the carriers will take place again. And then the majority carriers on N side will be minority on the other side after the diffusion, and the same goes to the P side as well. The holes in the P side, which were the majority originally, will then be minority in the N side after the diffusion process. So we have also learned that if your forward bias voltage is high enough, exceeding the turn-on voltage for the diode, or the knee voltage, which typically is about 0.6, 0.7, then the diode will be on, right? So if you are supplying a forward bias voltage of less than 0.7, for example, to the junction, the diode will not be turned on because the barrier, if you like, is not enough. This energy supplied is not enough. So you then have to supply enough voltage with the right polarity, bigger than 0.7, in order to induce the carriers to flow across the junction. And we've also discussed that, on the other hand, if you swap the polarity of the supply, so which means you are supplying positive voltage to the N side and negative voltage to the other side, and the diode will not be on, right? Because it's in reverse bias mode. And we've learned in the principle last time, when you are applying the reverse bias, you can see that the band diagram, if you want to relate back to the band diagram last time. So we are seeing that the increase in Berry height will keep increasing due to the reverse bias application to the junction, right? So that will, of course, hinder the carriers to continue to flow. But at the same time, we keep getting a very small amount of carriers crossing the junction. That will contribute to the leakage current, or we call it as J naught. So that will give rise to the J naught here. So if I can exaggerate a little bit, so it looks like that in the negative region. So this is typically in the region of picoamp or so, minus 12 ampere per cm squared. Okay, so we'll normally have this in our PN junction. In our every PN junction, we'll normally have some amount of leakage. If your PN junction is good, then your leakage current will be in the order of 10 minus 10 to 10 minus 13. So in the order of picoamp region, if you like. So on the other hand, if your diode is not so good, if your junction is not well formed, or your fabrication problem, for example, then it'll probably go up to microamp, 10 to the minus 6. So that's like 6 orders of magnitude higher if you compare to a good diode. Okay. So if you look at a PN, if you look at the JV curve, if you continue to increase the negative voltage, or if you're supplying the reverse bias voltage indefinitely, Okay, if you keep going to the left, at some point the junction will break. Okay, the junction will break. So that's what we call PN junction breakdown. So it's not on this illustration, it's not on this graph, but I've uploaded a material, a PDF file about PN junction breakdown. You can check, I think 2 days ago or so. So if you increase the voltage in the negative region high enough, your junction will break. And at that point, you're going to have an exponential increase of current in the negative direction. Okay, if it's too high. So you can label the voltage as VR, VBR if you like, or VR breakdown or something, V reverse breakdown if you like. So as long as it makes sense. So the exponential, the current will increase exponentially in the reverse direction, and that is called the reverse breakdown current. And that will happen when you supply a very high negative voltage to the PN junction. Okay, so at that point you're going to have exponential increase in current as well. We're going to look into that junction breakdown later on. Okay, yeah, breakdown only occurs at reverse bias. Okay, the moment you are talking here, the moment you're talking about the front, the forward bias, we don't say that it's under breakdown condition. We only say that it's under breakdown condition when you supply the reverse bias, because originally the reverse bias doesn't induce the current to flow. We don't want any current to flow in the reverse bias, and we don't get any current to flow after all. I'm talking about the conventional current, okay? I'm not talking about the leakage current. But we know that even though you are supplying a small negative bias to the junction, we do have currents in the region of 10 minus 10 to 10 minus 12 negative picoamperes per cm squared of leakage current. So that is the what we call the default condition when you're applying the negative reverse voltage to the junction. But if it's too big, if the voltage is too big, at some point, the magnitude depends on the type of material, the junction, the doping level, and so on and so forth. So there's no one fixed reverse breakdown voltage, if you like. So it depends on the many factors. So at some point, the current will just increase exponentially. It will no longer be in the region of picoampere. So it's going to go up very big, right? It can even go up to milliamp or ampere region, depending on the properties of the breakdown voltage of that particular semiconductor. So it happens only in the negative region or reverse bias region, okay? So all this while, we have been learning about a thick diode, okay? Thick diode. Let me improve this. So when we say it's thick diode, that simply means the diffusion length of your carriers is less than the device thickness. Okay, so kita buat summary sikit, thick diode, because now we're going to see the thin diode. So let's write a little bit about thick diode. So that's when the diffusion length of the carriers is less than the device thickness. Okay, well, you can imagine your device thickness is L, or if you like D, for example, you can write it that way if you want. You can put D, and this is D, right? The device thickness is the whole wafer thickness. So if you started off with a wafer, then you diffuse the junction on the front, the whole device is the whole thing, the whole wafer, right? Before you have your contacts on the front and contacts at the back, right? So anything between the contacts are the device. So in this case, silicon P and N is the whole device, right? So if your diffusion length of the carriers, electrons or holes, is bigger than the thickness of the device, so that means they can diffuse longer than the device thickness. So that means they will reach the surface of the device and get collected and contribute to the electricity, for example, or other device operation. Then we can say that they manage to survive. For example, if you are talking about hole, for example, if your hole is generated at this point and you want your hole to diffuse to the right hand side, any hole, hole H. So generated at this point. Remember the definition of the diffusion length is the distance traveled by a carrier from the point of generation to the point of recombination. From generation to recombination. The distance traveled is called diffusion length. The time possessed or demonstrated by the carrier is called carrier lifetime. Okay, the time is lifetime. The distance is diffusion length. Okay. So if you want your carrier to diffuse to the right, for example, and you want it to be reaching the surface on the right so that you the carrier can be collected by the metal on the left and on the right. We're gonna see the metals role later on in our next topic, metal semiconductor junction. Don't worry yet. So if you want your carrier to diffuse to this end, for example, in order to be collected at the metal contact and contribute to the IV curve and so on and so forth. So the diffusion length of this hole has to exceed this is only one side, right? One side. So let's go to the extreme. For example, if your hole is generated here, and you want to go to that contact on the right, for example, then technically you want your diffusion length to be larger than your device thickness, right? Your D, the small d. So you want your hole generated here to be able to cross and survive and collected at the contact. So in that case, we call that as a thick diode. Okay. On the other hand, if the diode is the diffusion length is less than device thickness, we can say that it's a thin diode. Okay. So now let's look at a thin diode, the impact of surface recombination on J0. Since we've been discussing about J0 for the thick diode on this page. Right? So let's recap and let's compare to this. This is for thick diode. Thick. Okay. What if the diode is thin? What is thin? Okay. So the above derivation of the J0 or the diode's J0 assume that the injected minority carriers recombine before they reach the diode surfaces. Okay. If the carriers recombine before reaching the device, the device end or the contacts. So maksudnya the carrier cannot survive through the device, full length or full thickness, if you like. We call that as a thick diode. So that means the diode is too thick and the carriers just cannot survive because the diffusion length is way too short in comparison to the device thickness. And we call that as thick diode, right? So on the other hand, if the carriers can survive, the diffusion length is larger than the device thickness. We call that as a thin diode. So in thin diode, the carriers can make it through the contact, up to the contact, because they can survive the diffusion. Okay. So if the minority carriers, on the other hand, can reach the surface of the diode, or basically whatever you have generated inside the device can reach both surfaces, we call that as a thin diode. Maksudnya distance traveled is just a simple distance, a short one, and the carriers can reach, for sure, can reach the surfaces of the N side and the P side. And in this condition, it's called a thin diode. And in this condition, the J0 becomes, so remember the J0 for the previous case, for the thick one is this, right, on this page. And now the J0 for the thin becomes a little bit more complicated because now the surface factor comes into the equation. Previously, the surface factor is not incorporated into the equation. Now it's in the equation already. So now the J0 becomes Q times surface recombination velocity. The S is surface recombination velocity times Ni squared. Ni squared is known over the looping level times the geometrical factor or the geometry factor. Geometry factor on one side and geometry factor on the other side as well, right? So both for Na and Nd, both for P-type and N-type. So the GF itself is given by this long equation. GFH and GFE, one for hole and one for electron. So the cosh of H prime over L for electron, and you can see the repetition of that, plus the S infinite, the surface recombination velocity for electron at over S of E time H prime over L as well, right? The H here is the thickness of the quasi-neutral regions. So where's the quasi-neutral region? So if this is your whole device, the depletion region is very, very small in the middle, and the whole thing here is the QNR for one side and QNR for the other side. So if you take this, you plus the other side, you're going to get the H prime. Okay, so the thickness of quasi-neutral regions. So for example, I mentioned a couple of times before, if you have a wafer of 200 micron thick, so the depletion region is probably 1 micron or less than that. So depletion region is like, if you assume depletion region is 1 micron, so that means depletion region over the whole thickness is like 1 over 200, right? 1 over 200 or 0.5 over 100, very, very small portion. So the rest of the volume of the material is actually the quasi-neutral regions, right? So that's actually approaching the device thickness. So basically the depletion region thickness over the whole device thickness is like negligible, if like, right? So the quasi-neutral region can be approximated to be equal to be close to the device thickness, right? Surface recombination velocity for E and H are the surface recombination velocities of the minority carriers. Okay, so when you compare this equation with the previous equation, you can see that in a thick diode, in the previous equation, let's revisit the previous equation. What time is it? 21. Okay. So if you look at this equation, do you see any surface recombination parameter in the equation? For this equation, for the thick diode? Do you see any S in the equation? Ada tak S in this equation for the thick diode? Ada kan? Very straightforward, right? Just look at the equation. What can we see is only Q, D, L, and I, and A, and D, right? So there's no S component in the equation. So that means when there is no S component, S component is typically related to the surface recombination velocity, okay? So as the name tells, surface recombination, right? Surface recombination velocities at the surface. So that's what it means. So in the previous equation for the thick diode, there's no surface factor in the equation at all. So that means regardless of what surface do you have, you can still do the calculation for a thick diode. So if a diode is thick enough and the diffusion length is shorter in comparison to the device thickness, the surface on the left and on the right, here, left and on the right, are not incorporated in the equation, which means both surfaces on the left and on the right are not important in a thin diode calculation. Okay. On the other hand, if we talk about the thin diode, you can see the GF. The GF is here, the geometry factor. Okay, and the geometry factor incorporates component of the quasi-neutral region and the diffusion length. Okay, and this quasi-neutral region is approaching the QNR thickness, or the device thickness, if you like. It's close to, because the depletion region width is very, very small in comparison to the whole device thickness, say 1 over 200 micron, which is very, very small. So in this condition, the surfaces of the device will be very, very important. So for example, if you talk about semiconductor device, kalau you tengok solar cell, for example, you can compare these two conditions as, if you want to say thick diode, then you can say, you can look at the solar cells or solar panels on the roof, which is based on silicon wafers that I showed to you last time, the blue one that I was holding during the class. Okay, on the other hand, if you are talking about the thin diode, we are referring to the solar cell as well, but the one that we have in our calculator, calculator sih tak ada ni. You ada kadang-kadang you ada calculator yang ada thin, ada amorphous solar cell tu kan, you nampak kan? Ataupun if you look at the smartwatches now, you can have some smartwatches with solar cells embedded dalam watch. And what else? We have some other gadgets with solar cells, or you have a charger untuk charge phone with solar cells, which use thin film solar cells yang pakai device thickness of like less than 1 micron if you compare to wafer yang pakai 200 micron. Okay, so you can equate that to this condition, right? The thick diode belongs to the thick solar cells, for example, and you can use the thin diode case for the thin solar cells, right? You can also use for other transistors, for example. Tapi transistor is typically well, we do have some. If you look at the conventional ICs, conventional IC dia biasanya is based on a thick diode, even though the active region is only on the top of the surface. We're gonna see in MOSFET later on. But we also have another transistors that we call TFT, thin film transistors, TFT. Thin film transistors. So transistor yang kita pakai for flexible devices, on the skin perhaps, right? Some other applications, right? So you can use this thick and thin diode calculation or approximation or the concept behind it, right? So now we know that the equation for J0 is different, and the surface factor is not important in a thick diode, but is very, very, very important in a thin diode. Okay, for what you call, to demonstrate this, let me draw something to you before we continue. We show the effect of surface factor. Is it clear now for the surface factor? Can you see the surface effects in thick versus thin? Is it clear? Forget about the equation first. Does it make sense now? In a thick device, the surface is less important. In a thin device, the surface is more important. Does it make sense for now? Anyone? Okay, let me just demonstrate one example. So example will make you clearer, I think. Okay, in a thick diode, okay, kalau if I can draw a small device, circle shape, we look at it at an angle, for example. Then say if you have a device like this, a wafer like this, so this is a thick case. Thick. Well, thin will be on the right. Thick on the left, thin on the right. Thick diode on the left, thick diode on the right. So if sorry, I forgot to share. Let me, tidak I lukis seorang-seorang. Okay, can you see it now? Can you see the sketch, the whiteboard? Okay. That's why I say selalu tanya, habis tu lupa tanya pula. So every time I normally ask so that we are on the same page. Okay, so thick diode on the left, thin diode on the right. So now I'm about to draw the thick diode example. Okay, so this is a circular wafer, for example. So if we are working on a thick diode, you can exaggerate. As we'll say exaggerate. It's not like this in the real life, right? So this is like your thickness of the device. Okay, so this is your D, if you like, device thickness. Okay, so this is your A, surface area, A. Okay, so that is a thick diode, right? So let's look at thin diode. The very same diameter of the wafer, more or less. Sorry for drawing. Okay, so now we are working on a thin diode. Okay. Okay, so this is your A. Belakang pun ada A juga, tak nampak kat belakang. At the back, this is your D. Okay. So now we know that we have A, surface area on the front side, surface area at the back side, and the D is the device thickness for thick diode and also for the thin diode. When you talk about thick versus thin diode, one important parameter is called surface to volume factor, surface to volume ratio, if you like. Surface to volume. Yeah, surface to volume ratio. So, for this particular case, if I want to simplify the surface to volume ratio, I can just write it as A over V. Total A, if you like, total A atas plus A bawah, A front plus A rear over V, right? Okay, surface to volume ratio, very simple. Just to demonstrate the thick versus thin diode mathematically, right? So thick versus thin, surface to volume ratio. Okay. So if you compare the surface to volume ratio for thick versus thin diode, which one has a higher surface to volume ratio? Thick one or thin one? Look at the equation and do a bit of math, simple math. Surface to volume ratio, yang mana lagi higher? Thick one or thin one? Which one is higher? Thin, okay. Anyone says thick? A over V. How do you calculate V for this cylinder? A times D, right? Volume betul. How do you calculate the volume of a cylinder? Area times thickness, right? Betul kan, Go? Area times thickness kan? Simple, right? Volume. So, okay. So, now the surface to volume ratio, which one has the highest one? Thin or thick diode? So many say thin. Thin highest, right? Anyone says thick? Okay, so majority says thin. Okay, more thin. Okay, when the surface to volume ratio is higher for thin diode, what does it mean? The surface is more important in a thin diode versus thick diode in comparison to thick diode, right? So you have a surface of A, but the D is very, very big for the thick diode. So A over D, or A over volume, if you like, will be very small because the D is very big. On the other hand, you have the very same A, but the D is very small now. So the denominator, which forms the D, which forms the denominator in this ratio, will be very small. So as a result, your surface to volume ratio will be very high. So at this point, your surface will play a greater role. Okay, or bigger role, which means the geometry factor will be more important in a thin diode versus thick diode. Okay, so can you see now? Just by this simple demonstration, forget the physics, forget the equation, forget the whatever, the J naught equation. Kat sini pun kita dah nampak kan? We can see clearly already the surface to volume ratio, right? So when you're talking about thin semiconductor device, surface to volume ratio will be very, very important. Macam you tengok duit shilling kan? If I have a coin here, okay, saya ada 20 sen ni, 20 sen. 20 cent there. You can see the cross section of 20 cent, right? The D is very small, the A is very big. And then if the D is very small, I think cross sectioning is if the D is very small. Okay, I'll come to your question, Hazik. If I see this, the D is very small, then technically the whole coin is the surface, right? Can you agree with me? Kalau D is very thin, then technically the whole coin is the surface. Tapi ni the edge is very small. You probably cannot, if it's too thin, then if you go to 5 cent, tak ada pula 5 sen, 10 cent lah. It's very thin. It's very hard to hold the edge. Okay, nak pegang area pun very small. The contact area is very small here. But the contact area is very big on the surface, right? So technically the whole surface is like surfaces, the whole coin. So the same goes to the thin devices as well. Okay, so is thin better than thick? It depends. It depends on where is the application for, right? So it depends on if you're talking about solar cell, for example, then if you're talking about thick, then we're talking about more volume for light absorption. If talking about thin, then we're talking about cheaper cost. Tapi if you go for a thick one, you have to spend more because you need to have such a very big D for your device. So there's a plus and minus for that, thick and thin, right? So there's no one single answer for that, right? Okay, let's continue. Let's go back to the PowerPoint. All right, so let's finish the thin diode and then we do a bit of calculation and then done. So can you see the slides now? Yeah, nampak? Okay, good. So for a given doping level, the geometry factor, the GF thing just now, the one given by this by the long equation, is fully determined by the two ratios S, the surface recombination velocity, and thickness of quasi-neutral region over the diffusion line. So if the H prime is more than 3L, typically, in this case, the surface has no effect on GF. So that means if you're working on a very thick diode, the H, the Q and R thickness is way bigger than the 3L. Typically, the surface is not in the equation at all. On the other hand, if your Q and R is very thin, lesser than the diffusion length, which means the carriers can reach both surfaces during the device operation, then the surfaces are very, very crucial in terms of the quality and the device physics and the approximation and everything. So GF plays a bigger role. Okay. So, well, you can play with the equation. You can look at the what we call the magnitude of the equation. If the GF, if your S is less than the infinite normally, so we're talking about 300 to 600 cm per second yesterday about the surface recombination velocity, then the GF is normally more than less than 1. So in this case, the surface has better electronic quality than the bulk, and the J0 can be reduced by thinning the diode, right? So this is another thing. When you ask this now, Hazik, about the thin, is it better or is it not as good as the thick? So if you're talking about J0, the leakage current, J0 will be lesser if you reduce the thickness of the diode. So that means if you're working on the thin devices, your J0 will be lower than thick devices. So at that point, your leakage current will be better in comparison to the thick one, right? But however, if you want to look at the device perspective, so you have to look whether the diode is going to be used for solar cells or lasers or LEDs or transistors or capacitors or whatever. And each of these devices, it has its own what we call performance parameters. Like for solar cell, you have to have short circuit current, open circuit voltage, field factor, conversion efficiency. But if you talk about integrated circuit, then you're going to have like drive current, rise time, blah, blah, blah. So totally different set of parameters. So it's hard to say a single answer as to which is better, thick or thin, right? It really depends on which application are we talking about, right? So if we talk about a solar cell, reducing the J0 by thinning the diode means improving the open circuit voltage. So we're going to learn later on in solar cell operation that this is the IV curve of a solar cell. So it looks something like this, just briefly. So here is the IC or short circuit current, and this is the intersection here is the VOC, open circuit voltage. And you want the short circuit current to be high and the VOC to be high as well in order to produce highly efficient solar cell. So by reducing the J0, by reducing the thickness of the device, you can reduce the J0. So J0 will reduce. If you reduce the device thickness, J0 will reduce, and this will increase the VOC, the open circuit voltage. And this will increase the efficiency of the device. So this is only applicable for solar cell. So when you talk about MOSFET or JFET or BJT or some other devices, we really have to go down to the parameters of the device in order to analyze whether thick or thin is better. Okay. So let's try this question now before we finish. What time is it? 1:40 already. Okay, come on. Have you tried this question already? Let's spend about 10 minutes maybe on this. Okay, a PN junction is formed in silicon with Na, right? Na 1.5 times 10 to the 16, and Nd 5 times 10 to the 19, right? So N-type there is 5 times 19, and P-type there is 1.5 times 16. So 300 Kelvin intrinsic carrier is 1 times 10 to the 10. We know this already. Assume that the P-type and N-type layers are infinitely thick. Apa maksudnya? What does it mean? P and N-type layers are infinitely thick. What does it mean? What can you relate this with? Apa maksudnya? What does it mean? Thick diode, right? N-type and P-type, the quasi-neutral regions, Q and R, which is 98, 99% of the whole device thickness, right? Assuming that the depletion region is like a couple hundreds of nanometers. Minority carrier for electron hole diffusion lengths are LE 100 micron, LH 500 micron. Mobilities of electrons and holes are 1300 centimeters squared per volt second for electrons and 30 centimeters squared per volt second for hole. So question number 1, calculate the built-in potential of the junction. Right, anyone? What did you get? Come on, let's be quick a little bit. Now 1:42. Let's spend about 5 minutes or 10 minutes or so for this question. So anyone who's got the voltage, what's the VBI, built-in potential? Faris, what did you get? Faris, what did you get? Right, 0.94 volt. Okay, anyone else got the same answer or different answers? Ada yang dapat lain? Same, right? Anybody with different answers? Sama? Lagi? Right, can you see the word file? I'm sharing on the screen now. Can you see? Okay, nampak? So the same thing. So what you have to do is simple. Use the VBI equation, KT over Q ln ND times NA over NS squared, right? So the answer is 0.94 volt. Okay, the second one. Calculate the concentration of majority and minority carriers at the edge of depletion region in N-type and P-type of the junction under thermal equilibrium. Okay, majority and minority of both sides under thermal equilibrium. So how many answers are expected here? How many answers are expected for this question? 4, right? So 2 majority for P-type and N-type, 2 minority for P-type and N-type as well. Okay, under thermal equilibrium condition. There's no voltage applied or whatsoever. Okay, so what do we get? Check this out. Zero voltage applied. Majority populations are given by the doping densities. PP naught kita belajar sebelum ni. PP naught is approximately equal to Na, right? PP naught approximately equal to Na at the thermal equilibrium. Remember the three things there. PP naught, density of holes in p-type at thermal equilibrium. Three things, PP naught or Nn naught. So therefore, PP naught is Na 1.5 times 10 to the 16 per centimeter cube on the p side. And the Nn naught is equal to Nd 5 times 10 to the 19 per centimeter cube as well on the N side. So next, to be able to calculate the minority carriers, we need to use the law of mass action. So NP equals Ni squared. Majority carrier populations are given by the law of mass action. NP naught equals to 6,600 plus, right? Betul kah? Did you get 6,600 plus? Betul. Okay. Okay. Anybody got different answers? Sama. So the first thing to do is write down your majority carriers. Okay, write down the majority carriers, Na and Nd, which will not change. Okay, dia akan sama aja untuk setiap soalan. Then you just have to calculate the minority carriers accordingly, right? And for Pn naught, terbalik ni bukan the N naught supposed to be subscript, not superscript. Pn naught is about 2 per centimeter cube on the N side. Okay, so let's go to the next one. Calculate the concentration of majority carriers and minority carriers at the age of depletion region in the N-type and P-type with a forward bias of 0.6 volt. So what do you get? Forward bias of 0.6 volt. So which equation do you use? So the one with the exponential component, right? The QV applied bias over KT. So what do you get? Okay, Shamimi, what did you get? So do we have a change of majority carriers for P-type and N-type? Do we have a change of majority? No. Okay. So what's the minority carriers? Okay. So Pn equals to Pn naught. So Pn naught is calculated already, right? So you've got this. Pn naught is 2 and Np naught is 6,700 more or less, right? Kalau you bagi yang the exact number pun okay. This one pun still okay. So, but you have to get this right first before you can move on to the next calculation. If you don't get your thermal equilibrium values to be right, then your other values in the bias condition will be wrong. Okay, you have to get it right first at thermal equilibrium. So even though if it's not us, please calculate the values at thermal equilibrium first because it's going to be involved in the equation as the Pn naught or Np naught thing, right? Then only you can move on to calculate this under bias condition. So we dapat Pn 2.39. Yep, that's okay. 2.4 lebih kurang. So I think this is on the decimal places thing. Kalau kita round up or pakai many, then you're going to end up with a more accurate answer. So Pn equals to Pn naught is already calculated in the first question. In the second question is now exponential of QVA over KT. VA is known, Q over KT are known, so we can get the answers, right? 2.4 more or less. So the NP about 8, right? 8 times 10 to the 13, right? So semua dapat sama? Same answers for all? No answers different, yeah? Okay, the majority carrier concentration increased by the same amount as the minority carriers in order to maintain space charge neutrality. However, the change in majority carriers is small compared to the concentration of the ionized dopant. So remember last time when we did the P equals to P naught plus delta P, right? Or N equals to N naught plus delta N. We have seen that the change of the delta N or P is way too small in comparison to the majority carriers, which makes the majority carriers remain the same. But you've got a change of minority carriers due to the illumination or applied bias accordingly, right? However, the change in majority carrier is so small, blah, blah, blah. So the N side and sama lagi, and ND is, the minority is given by this PN and NP thing. Next, how much forward bias voltage is required to increase the minority carrier densities at the edge of depletion region by a factor of 10? Okay, what did you get for this? How did you do this, by the way? How much forward bias is required to increase the minority carrier densities at the edge of depletion region by a factor of 10? You got the same equation. You have to use the same equation, but now the Pn over Pn naught. Say you can what you call manipulate the equation, right? Pn equals to Pn naught over exponential of Qv over Kt. So you can rewrite this equation as Pn over Pn naught equals to exponential component, right? Good. And Pn over Pn naught is the ratio of increase. If you compare to under bias condition versus thermal equilibrium, right? If the comparison is 10, the ratio is 10, then the Pn over Pn naught should be 10. Okay? So minority carrier at the edge of depletion region changed by a factor of exponential QV over KT. Remember last time we discussed about when you increase the amount of applied forward bias, the minority carriers at the end of the depletion region will increase accordingly, right? The VA error last time, remember? You increase the VA, so you're going to end up profile macam ni kan? Majority cross the depletion region, and then it's going to go down, right? Exponential decay. And this decay, the gradient will become like that, will increase. This point at the edge of the depletion region on the opposite side will increase accordingly when you apply the VA. Dia akan jadi less steeper, right? So this is the increase of the carrier. So dapat tak, Haziq? Faris, can you share your answer? Can you explain a little bit verbally? What did you get? How did you get to the 60 millivolt? I think you got it right. Tak apa, it's okay, it's okay. It's just a matter of decimal place. Can you explain how did you get to the 0.66 volt? Oh, you get it 660 then. Oh, it's not 0.066. Okay then. Oh, but how did you get there? How did you get the 0.66? What did you do? I'm PNB, so that means your PN over PN over PN, you over PN thermal equilibrium or PN under first bias condition? How about others? So you rearrange the equation, then get VA. Okay, how about others? And anyone got 60 millivolt or 0.066 volt? Anyone? How about Fatin? Fatin dapat tak jawapan? Fatin Tahira. Did you get it? How about others? How about Go? Did you get it, Go? Did you get 60 millivolt? Oh, tak dapat. Okay. How about others? Apa lagi? Juaria dapat tak? 60 millivolt? Oh, tak dapat juga, eh? So, okay lah, tak apa, nanti saya bagi dia punya jawapan yang panjang sikit. So, what you have to do is you have to ratio the new concentration. Well, the new concentration is not given, right? But we know that the ratio is 10 times higher. So if you look at the previous equation, Pn naught, so the ratio of Pn over Pn naught is, say, 10 times. Okay, 10 times. Then you can just do the calculation of VA accordingly, right? Nanti saya share dekat e-learn. So, but if you do the rearrangement using Pn over Pn naught equals to 10 for the minority carrier, you're going to get VA equals to 60 millivolt or 0.066 volt. This is a share. Right, the final one, calculate the minority carrier concentration at the edge of the depletion region in N-type and P-type of the junction with a reverse bias. Now the V becomes negative 0.06. Okay. So you use the same equation, Pn equals Pn naught. Okay, Pn equals Pn naught and Np equals Np naught exponential QVA over KT and plug in the negative 0.06 volt. And then you're going to end up with 0.2 per centimeter cube for minority hole concentration in N-type and 654.5 for minority electron in P-type. So if you compare this with 0.2 Pn 650. So if you compare this, just to get back to the what I call the fundamentals. So if you apply forward bias 0.6 volts, then you're going to end up with, look at these values, Pn versus Np. Pn will increase to 2.4 times 10 to the 10. Forward bias 0.6 volts. And the Np will increase to 8.02 times 10 to the 13. 10 to the 10, 10 to the 13. Forward bias 0.2. If you reverse bias, look at the value now. The Pn, forward bias 10 to the 10 now becomes 0.2 in reverse bias 0.06. And the Np goes down to 650. Okay, so whenever you've got your answers, you also have to check with the fundamentals, right? Whether it makes sense or not. So some students last time, they did the calculation, but then they didn't cross-check with the principle behind it, right? Forward bias, this much. Reverse bias, this much. Does it make sense? Does it make sense? If you compare the forward and reverse bias now, does it make sense? The values of both? Makes sense now? In terms of the magnitude. Makes sense, right? If you do forward bias, and then you're going to end up 10 to the 10, 10 to the 13, because carriers are crossing again, right? Because the effective Berry height is now reduced. So the carriers can now diffuse to both sides, to the opposite side. On the other hand, if you stretch the reverse bias voltage to negative 0.06 to the left-hand side of the JV curve, if you want to relate with the diode equation, then you're going to end up with a very small amount of carriers. Pn is only like 0.2 and only 650 for Np. So it makes sense. So if you do your calculation and you get these values, Pn and Np, to be way bigger than this, then you have a problem. The calculation has a problem. Okay? Whatever you learn here in this course or physics generally, so most of the cases, they make sense, right? Most of the cases, they make sense. With some condition, maybe you cannot imagine or is beyond our comprehension in some condition, then maybe it's hard to make sense of things. But in this condition, you have to be able to make sense of things. If this gives you much bigger value than this, then the calculation is in trouble. And you won't be able to explain after all, okay? So I'll share this and a bit of elaboration maybe on the ratio of the 60 millivolts. Nanti saya akan share dalam e-learn. This one is only a brief one, just to discuss. Okay, so 158 already, okay. So right, done for today. We're going to move on to, tomorrow is Thursday. I'm going to continue tomorrow with the junction breakdown a little bit, and then we're going to go straight to the PN junction under illumination. Okay, then we are done with the physics more or less of the course. And then next week we're going to look into the metal semiconductor junction. So all this while we've discussed about the PN junction itself within the depletion region, away from depletion region into QNR. Now we're going to talk about this interface and this interface between semiconductor to metal, right? When we want to extract the carriers out of the semiconductor to the outer circuit. So we're going to have like another band diagram, work function, barrier height, all the stuff again. After finishing the topic, we're going to start going into the devices. Okay? So any questions for now? Is it okay so far? Yang mana yang belum attempted the calculation, please do so for your own good, not for my good. Okay? Soalnya saya selalu pesan dalam kelas dekat third year, fourth year student. I normally say a simple thing to the student. Third year, fourth year, normally I don't have to chase you already because you are big enough, you are senior enough, I would say, and you're going into the job market, you're going to work, you're going to start a career in like 1-2 years time. So there's no point chasing you to do your stuff. It's your responsibilities, right? For your own life. So not for my own good, for your own good, right? And if the students take it positively, they'll go and do it themselves. If they don't want to take it positively, then entirely up to you, right? You're big enough to think about this, right? So I'll see you tomorrow to continue with the junction breakdown and then the next topic. Okay, tak ada soalan, huh? Okay then, bye-bye. Take care. Assalamualaikum.